I am Dr. Jawed Ahmad, Jamshedpur Women's College, Jamshedpur. In this video, we are going to discuss concept of limit point of a set, which is for the semester 2 honors students, paper 3 of real analysis. Now let us see what definition says. Definition is a real number a is said to be a limit point of a set S, which is a subset of R, where R is the set of real numbers, and students are familiar with the set of real numbers. If every neighborhood of a point A contains an infinite number of member or points of the set S. Again we are repeating, a real number A is said to be a limit point of a set S, which is a subset of R, if every neighborhood of the point A contains an infinite number of member or points of the set S. Thus the real number A will be a limit point of a set S if for any neighborhood n of A, n intersection S is an infinite set. This definition can be stated like this also. A real number A is a limit point of a set S, which is a subset of R, if every neighborhood of the point A contains at least one member or one point of the set S other than the point A. A limit point is also called a cluster point or a condensation point or an accumulation point. Limit point of a set may or may not be a member of the set. First condition is. Further, it is clear from the definition that a finite set cannot have a limit point. Also, it is not necessary that an infinite set must possess a limit point. In fact, a set may have no limit point, or a unique limit point, or a finite or infinite number of limit points. This statement says that an infinite set may have a limit point or may not have a limit point. If the limit point exists, that may be unique or finite number of limit points a set may have, or infinite number of limit points a set may have. A sufficient condition for the existence of limit point is actually provided by Bolzano-Weierstrass theorem that we will see in the next video. It is instructive to note that a real number k will not be a limit point of a set S if there exists even one neighborhood of k not containing any point of the set S other than k. The set of all limit points of a set S is called derived set and is denoted by the symbol S dash. First, we shall prove that a non-empty finite set has no limit point. For this, let us consider a very small set like A is equal to the set containing the points 1, 2, 3. There exists a neighborhood 1 minus epsilon, 1 plus epsilon of 1, which is a member of A, contains no point of A other than 1. Actually, the neighborhood of the point 1 contains infinite number of real numbers and which are not the members of the set. So we see that the neighborhood of any point 1 contains no point of A other than 1. So 1 is not the limit point. 1 is not the limit point of the set A. Similarly, we can see or we can generalize that a finite non-empty set has no limit point. Let us see the next example. The set I of integers, which is actually an infinite set, and we are going to discuss about whether the infinite set has limit point or not. Each infinite set needs not to have a limit point. It is not necessary, and we will say after taking different examples. First we take example of integers, that is set I of integers has no limit point, because for a neighborhood m minus epsilon, m plus epsilon, or you can take m minus half, m plus half, where epsilon is a very small positive number, of m belongs to I. We have taken a member m of the set of integers, arbitrary member m, which is a member of I, and m minus half, m plus half, or m minus epsilon, m plus epsilon, it is a neighborhood of the point m and contains no point of I, because like before, between these two endpoints m minus epsilon, m plus epsilon, there are infinite number of real numbers, and these real numbers, all these real numbers need not to be an integer. So you can say that this open interval or neighborhood of the point A m does not contain infinite number of members of I, that is, it does not encloses infinite number of integers other than m. So we can say easily that the set I of integers has no limit point, and clearly the set formed by the limit points of I is empty, and we say that derived set of I is the null set phi, that is I dash is equal to phi. We can take next example, that is set of real numbers, and like above, by considering any arbitrary real number x, we form a neighborhood x minus epsilon, x plus epsilon of x belongs to R, and clearly it contains an infinite number of members or real points of R, and hence by definition x is a limit point of R. But x is an arbitrary member of R. This proves that every member of R is its limit point. So set of real numbers is the set which is whose all members are its limit point, and that's why we write R dash is equal to R. That is the set of limit points of this set of real numbers is the set itself. Similarly, we can prove that Q dash is equal to R. Here Q stands for the set of rational numbers and Q dash stands for the set of limit points of the set of rational number. and this is left as an exercise for the students. Thank you.